That's multiple.
So we're going to start Ampere's law. Okay. So let's please discuss it and then see how far we can get. Hopefully we'll finish it. I'll do at least 2 examples. Okay. So Ampere's law. I'm going to state the law. I'm going to write it in mathematical form, and then we will discuss what it means and how to apply. Okay. You can't prove it; it's a law. So B dot ds closed loop integral of B dot ds is equal to mu naught times the current through the loop, or enclosed. Some books call it enclosed, some books call it through the loop. So let's see what it means. Okay? So that's the statement of the law. Okay? Now we're going to discuss what it means. Okay? So here's let's suppose this is the current I. The current I. And I'm going to draw a loop around it. This is not a surface, it's just a loop. It's a 2-dimensional thing. It's just a loop. It's not an actual wire or anything, just a mathematical loop. So this is the loop. Okay, that's my loop. I'm trying to make it a random loop, but it's not quite random. Okay, all right, random enough. Okay, so that's the loop. So the current through the loop is I. So I have a loop, and I ask, is there current coming out through my loop? Yes. If I draw a loop here, here's another loop. Is there current coming out of this loop? No. So if for that loop, the right-hand side is 0 for this loop. For this loop, the right-hand side is got mu naught I. Okay. So, but you could have I. Let's call this one here I1, and let's say I have another current I2, but I2 is going in. I2 is going in. Okay. So would I say I would just add them? Let's say one of them is 7 amps and the other one is 3 amps. Do I just say 7 plus 3, which is 10? Or I need to subtract them? They're in opposite directions. So somehow I have to subtract them. Okay? So we're learning the rules on how to apply Ampere's law. So Ampere's law says, yes, if you have one coming out, one going in, you have to subtract them. How do you subtract them? Which one would be the positive, which one would be negative? So it depends on how you do. If you go counterclockwise, let's choose, if I go counterclockwise, let's say for this loop here, this loop is counterclockwise. Okay? If the loop is counterclockwise, then I1 is positive and I2 is negative. So if the loop is counterclockwise, CW, right? Counterclockwise, then I1 is counted as positive, I2 will be counted as negative. Okay.
Do you mean the magnetic field?
No, the current.
Current?
Yeah, I haven't discussed magnetic field yet. I'm just looking at the right-hand side. Oh, okay. So the current is either positive or negative. So let's give them some numbers just to, let's say this one here is 7 amps, and this one here is 3 amps, right? So for the red loop, so for loop 1, which is this with red, I enclosed is equal to what?
I1 minus I2.
I1 minus I2, so it would be 7 minus 3, so it's 4, right? 4 amps. That's how you count. How about somebody else chooses a different loop? Let's say we choose this loop. And now this loop is going clockwise. See, this loop is clockwise. So loop 2, I enclosed is would be what? But now I have to count them the opposite.
So 3 minus 7.
Yeah, it would be minus 7 plus 3, So it's equal to minus 4 amperes. Okay? Minus 4 amperes. Now think about why that's the case. Right? So think about why that's the case. So this loop, this one, the loop number 2 is clockwise for me, right? For us, we're here. Let's say somebody goes behind. That loop is counterclockwise, right? This loop, if you go behind the board and look at it, how does it look like?
Counterclockwise.
It's counterclockwise. So for you, if you go behind the board, I1 will actually be doing that, right? It's going into the loop, and I2 will be the one coming towards you. So anyways, if you go clockwise, if you go counterclockwise, the currents that come out are positive. The currents that go in are negative. And we usually loop counterclockwise. Yes?
By like looping counterclockwise, are you saying when the magnetic field goes this way, that would be positive?
Goes how?
So like with I1 right here,
So if the magnetic field goes counterclockwise, it's positive. Yeah.
positive. Okay, so that's what we're doing by loop.
Let's focus. So for now, it's the right side. I'm going to get to the left side now, and I will address your question. Yes.
Can we still use the right-hand rule for figuring this out?
Right. So so essentially, that's what I'm doing. A current that comes out, and I go counterclockwise. That's come to this positive. So next, I'm going to look at the left-hand side. Okay. How do we do the left-hand side? Okay. Let's look at the left-hand side, and so let's draw a current here, I. Let's say I1, I have I2, right? I2, this again 7 amps, this one here 3 amps, and I'm going to choose a loop that looks like something like this, okay? So now we're going to check the left-hand side. So the right side, I'm going to just say mu naught times what? If I go counterclockwise, it's going to be times 4, right? Because I that's coming out will be 4. Okay. So I'm going counterclockwise. So let's see what ds is. Suppose I commit to counterclockwise. Usually the default is we go counterclockwise. Okay? Usually we just go counterclockwise. So here's ds. ds is going to be this way. This is a ds here. Here's ds. So ds is tangential to the loop. This is ds. Okay. So ds is tangent to the loop. So that's what we mean by ds. Okay. Right. So let's do a specific example that we know the answer to, just to apply Ampere's law. Here is a specific example. Let's say I just have one current that's coming out called current I. Okay? I need to choose, so I want to apply Ampere's law. First, I need to choose what's called, remember Gaussian surface? Amperian loop. Okay, the loop is called an Amperian loop. It's not an actual physical wire loop, but a mathematical loop. And the question is, how do we choose the loop? What kind of shape should we choose? And I think you would guess it's a circle whose center is I. You wouldn't choose a rectangle, and I will show you why in a second why you wouldn't choose a rectangle. I'll go back to it. But let's choose a circle. Why? Because we already know the current for an infinite wire from the Biot-Savart law, right? For the Biot-Savart law. For example, if the current is coming out, in what direction is the magnetic field in this case? Counterclockwise. Okay. So we're going to ask. So let's look at this. We're going to ask the following: our goal to use Ampere from using Ampere's law is mostly to find the magnetic field. So let's choose a point here. We're going to ask the magnetic field at this point versus this point versus this point, as long as they're the same distance from the wire, do you think the magnetic field will have a different value? No. From the symmetry, there is no reason the magnetic field here would be preferred over here, as long as you're the same distance. So that's why, or part of why you choose a circle. So we choose a circle. So my Amperian loop is going to be a circle. I'm going to draw it. Okay. And that circle will have a radius r. That's the circle. Now ds will be tangential to the circle. Here is ds. ds is going to be tangent to the circle. These are the ds, right? Next, we're going to guess the direction of the magnetic field. Magnetic field, there are two choices based on the symmetry. In what direction do you think the magnetic field would be? It would be counterclockwise, right? Maybe clockwise, or maybe radially outward. That cannot be just radially outward, because I will show you when we do Gauss's law for magnetism. Magnetic field can just be coming out. It means you just have a north pole, okay, by itself. If it comes out, it has to come in from somewhere. You can't just have it coming out. If you have it coming out, it means you have just isolated the north by itself. So it can't be radially outward, so it has to be in the tangent direction. It could be clockwise, it could be counterclockwise. I'm going to just guess counterclockwise because we already know if I have the current this way, the magnetic field is going to be. So it's going to be counterclockwise. So let's see how we can apply Ampere's law. Here's Ampere's law. Yeah, we say V dot ds equal to u naught I A plus. Yes.
Like with resistors, did you be able to at some point know whether you chose the wrong direction?
There is no resistance. This is just direction of the magnetic
Like
field.
with resistors, how you would get a negative.
Oh yeah, yes. Let me come back to that in a second. So B dot ds, we already said, we're guessing the magnetic field is going to be counterclockwise, right? If our guess is correct, we get a positive answer. If our guess is wrong, we get a negative answer. So let's see. So B dot ds, we need to do this dot product. Let me look at the right side first. What's the current coming out from this loop? Just I. So it's going to be u naught times I, however much I is, okay? Left side, in what direction is ds? Counterclockwise, tangential. In what direction is B? Same. So what's the dot product of two vectors that are in the same direction? They're perpendicular is 0. Yeah, so it's just their product of their magnitudes. So it's going to be B times ds. Now, B, this is the magnitude of B. Is the magnitude of B constant or changing as I go around the circle? Yes, as long as the radius is fixed, it's constant. That's why you wouldn't choose a rectangle. If you chose a rectangle, the distances would be varying, and also the dot product you can do. Right, it would be different angles. So we can pull out B.
If you chose a square, would you have to do
Yeah, and then the angle is going to be different. So we got ds, mu naught I. Okay, what's the integral of ds? S. And how much is S?
Pi d.
Yeah, the length of the circle, right? Which is, you mean the circumference of the circle?
Yeah.
Which is?
Pi to r.
Yes. And we already had this result. This is much easier. To your question, I think you said if you choose a square, yeah, the angle is going to be different, right? ds along this line is going to all be this way, but the magnetic field will have different angles, right? So it's not going to be a nice integral. So generally speaking, you would have circles, maybe a rectangle. We will see when we have those. that's that. Yeah. You're interested in force? Think about it and then, yeah. Okay. Yeah. So that's that. Next question is going to be a thick wire. See, this one is a thin wire. We're going to do a wire that's thick, like a bundle of wires. All of them have a current coming towards you, like this. So thick wire, thick wire, of radius R. See, this one, if we try to do B sub R, good luck. Yeah. Hard. So here's what I mean. So here's a wire. The radius of the wire is R, okay? And let's say the current is coming towards you, meaning this. So the current is just coming towards you. I'll draw enough of these just to demonstrate the point. Again, these dots are referring to what? Current or magnetic field?
Current.
Current, good. So the current is coming towards you. I started when I finished, right? Okay. Okay. Almost there. That's enough. So the current is coming towards you. Okay. And the question now is, what's the magnetic field inside the wire, and what's the magnetic field outside of the wire? And you see how horrible that is with BSFR. You have different DS's and different R's, and then the DS's are on different wires. It's just, yeah, not going to be very nice product. Okay. So that's how it goes. I'm going to now redraw this, but without all the currents. So here is this is the wire. This is an actual physical entity, right? This is the wire, and there is current coming up. So let me remind you of J. Who remembers J? Current density, which is what? Current divided by
Area.
by area, yeah. By area. What's the by area? Let me write. What's the area of this wire? Pi r squared. Yeah, pi r squared. So that's the current density. The reason I want to refer to the current density is because I'm going to draw an ampere loop and then ask how much current is coming out of that ampere loop. So I'm going to start with inside the wire. We'll do the difficult part first. Inside the wire means little r is less than capital R, right? So here's the ampere loop. It's going to be here. Okay. And we're going to choose our loop to be counterclockwise again. The default is always counterclockwise. Not always, but I like counterclockwise. Because we kind of also know the current is coming out, so chances are the magnetic field will be counterclockwise. And we're going to write Ampere's law. B dot ds is equal to mu naught times the current that's coming through, or the current enclosed. In this case, you cannot say the current enclosed is I, because look at your loop. Only part of I is coming out, right? So only the part of the current that's within this area would be coming out. This area is little r. I mean, the radius is little r. So, huh? Yeah, it is a circle. Yeah. So, how much current is coming out? It's mu naught times what?
J A.
Current density times the area, right?
Yeah.
Of that red loop. Yeah. The current density times the area of the red loop. Because, for example, if the area of the red loop is half the area of the wire, how much current do you get out? Half. Yeah. If it's a third, it's a third. So it's proportional to the ratio of the two areas.
Yeah.
So it would be mu naught and then J times the area of this, of the red one, so pi r squared, and so you get mu naught. I'm just working with the with the right side for that. You have I over pi r squared, and now let's look at the left side. Oh, pi. Left side. Magnetic field, in what direction? Clockwise or counterclockwise? Those are the only two options, okay? So B dot ds is going to be, what's the dot product of B and ds? ds is counterclockwise and B is counterclockwise, so their dot product, B ds. Is the magnetic field value going to be changing at all? No. So it's going to be just B times ds, right? What's this now? B times
2 pi
pi r.
r.
Just like Gauss's law, right? It happens a lot with that B dot d or E dot dA in that case. So now a pi, one of these r's, this r, so you get B equal to mu naught times I over r 2 pi r squared times little r. That's inside the wire. How about outside? Huh? Yes. I hope it's it would be like this one, and we'll show in a second. But it's similar to Gauss's law. Remember, for a sphere, once you exit the sphere, how does it behave? At the point charge. Once you exit the wire, it will just look like any thin wire. Yeah. So inside or outside, for little r greater than capital R, draw now, here's my ampere loop, right? Here's little r. We're going to go, again, counterclockwise. So the current that comes out is positive. So we get E dot ds is equal to mu naught times I enclosed, or I through. How much current comes through now? Yeah, all of it. Yeah. The whole current comes out. Okay. Yeah, so just mu naught I. Left side, B dot ds becomes B ds. B comes out, B times 2 pi r. Yeah. B times 2 pi r. So B equals mu naught I over 2 pi little r. That's the magnetic field. This one is for r greater than r. Going to plot it. Look at this. What's the magnetic field when r goes to 0?
0.
0, and then it will grow, right? As r gets bigger, the magnetic field gets bigger. And how will it grow?
Linear.
Linearly, good. Right? It's some stuff, constant, times r. So it's linear. It goes like this. What's this point here?
Yes.
Yeah, r equals big R, which is mu naught I over 2 pi r, right? Because r, yeah. So mu naught I over 2 pi capital R. Now when you're at the surface of the wire, now you're outside. Outside, this one applies. Also drops as well. Yeah. It goes like this. Okay. Any questions on this application of ampere as well? Worksheet 12, I think, has some ampere laws there. Yes, John.
Is the current density constant in this case? Or?
Yeah, it is constant. Yeah.
So if it's not constant, then we're going to be able
It
to
becomes an integral. Yeah. Yeah, that if it's not constant, but usually it's constant. Okay. Yeah. describe the solenoid and then go from there. We will finish the solenoid in discussion, and then next time we're going to start with Faraday's law. So I think that's chapter 29. Yeah.
I wonder what's the directions of the magnet field.
Counterclockwise.
Oh,
Yeah.
oh yeah.
So solenoids, how does a solenoid look like? Looks like this. The cross section doesn't matter. It could be circular, it could be rectangular. But let's just choose a circular one. So this is the core. It could be plastic or wood or something. And you wrap a wire around it. Just wrap a wire around it. And the solenoid, an ideal solenoid will be infinite. However, if it's long enough, then it's infinite enough and you can use the approximation, right? If it's, for example, if it's 2 meters this way, and this one is just like a couple centimeters, so it's much longer this way than this way, and therefore we just say it's an ideal solenoid. It's approximately ideal, right? Just like with the wire is never infinite, but if it's long enough, then we're up. Okay. So here is 4. And what you do is you take a wire, and you wrap it. So here's the wire. Okay. And then this is your wire, and then later you can connect it to a battery or something. Okay. So if you connect it to a battery, there will be a current, and the current will just be going like that, right? Or like this. It doesn't matter. Depends on how you connect. The bottom line is, because there is a current, it's like you have many loops, and we're inside here, and there will be a magnetic field inside. You will see. Yeah, almost. Yeah. So that's the solenoid, right? This is a solenoid. So the solenoid, usually, a real solenoid will have a length L. The length of the solenoid is L. It's not infinite, but it's long. So that's the solenoid. So capital N will be the number of loops. Right? So let me ask the first question. How would you know the length of the solenoid?
Given.
Huh?
It's given. It will be given.
It will be given, yeah, you measure it. Get a meter stick and measure it. Okay, yeah, good. And now the number of loops, how would you know the number of loops? Yeah, count them, good.
What?
That's it. You made it, so you counted how many loops. So N is given, L is given, right? So L is the length of the solenoid, and N is the number of loops. Little n is the density of those loops. It's the total number of loops divided by the length. Okay? Total number of loops divided by the length. So for instance, let's say your solenoid is 1 meter long. Okay? Solenoid is 1 meter long. Okay? And let's say you wrap 10,000 loops. 10,000 loops, right? Regular 10,000 loops. So you have 10,000 loops per meter, right? You have a total of 10,000 loops over 1 meter, 10,000 loops per meter. So if I just get 1 centimeter, how many loops do I expect to be on 1 centimeter? 100, right? Because there are 100 centimeters in a meter.
1,000.
100 times 100 is 10,000, right? So there will be 100. So it's little n tells you the density of the loops. How densely packed are they? Like how tightly did you make them? Are they just far apart, or are they densely packed? Okay. Okay. So what's the goal is to find the magnetic field outside the solenoid, inside the solenoid. Okay. This shape is called the solenoid, by the way. How do you spell it? Yeah, they have to be. Yeah. So I'm going to. So solenoid. I will just give you the result. We will talk about how to show the result using Ampere's law. Inside the solenoid, inside it, magnetic field is mu naught little n times the current. Mu naught little n times the current. Outside, I'm just giving you the result. Outside, magnetic field is 0. Again, I haven't proven it, but we'll show it. Yeah.
And you said this is the same thing as an MRI?
I didn't.
An MRI is a type of.
It uses some magnetic field related to a solenoid. Yeah. Yeah.